Hello, welcome to part 2 of our lecture from chapter 10. In this part of the lecture, we'll talk about energy. Specifically, we're going to talk about kinetic energy, potential energy, thermal energy, and total mechanical energy. Let's start by talking about kinetic energy. So what is energy? Well, we have a couple of definitions here that we're going to work with. The first one is sort of a non-technical definition, but we can say that energy is the stuff that is transferred when work is done. Now, what do we mean by that? Well, let's take a look at this animation here. We've got the guy that gives this shopping cart a shove. He pushes it and it rolls across the store. So basically what he has done by pushing on the cart, he has done work on the cart. And what happened when he worked on the cart is he transferred something to the cart that it didn't have before. And that something is energy. So that's what we mean that energy is transferred when we do work on an object. Now, we can take this a step further and think about what does this moving cart do as it rolls across the store? Well, imagine this cart bumped into another cart that just happened to be sitting there. Well, our moving cart would then do work by creating a force and pushing on this cart. And therefore, by doing work on the second cart, it would transfer energy to the second cart. So this is sort of a functional definition of energy. Energy is the ability to do work. And this is really the important and practical definition of energy because this is the way we use energy in our daily lives. When we eat food for energy, that food energy gives us the ability to do work. When we put fuel in our car, that fuel then has the energy which has the ability to do work so that our car can drive and so forth. So the first type of energy that we encounter here in this course is called kinetic energy. And kinetic energy is the energy due to motion. The word kinetic means moving. So kinetic energy is abbreviated by the letter K, and it can be calculated as 1/2 times the mass of the object times the velocity of the object squared. Now, if you're wondering where this formula comes from, I'll show you briefly on the next slide, but we're not as interested in the derivation of this formula as just being able to use the results here. So kinetic energy, or all types of energy, interestingly has the same unit as work, and that is it is measured in joules. And there's a reason for that that will become more apparent later. So let's do a simple example here. What is the kinetic energy of a 150-gram baseball thrown at 30 meters per second? So we know that kinetic energy, K, is equal to 1/2 mv squared. So we have to make sure that the mass here is put into kilograms to use our equation up here. So 150 grams is 0.15 kilograms because there are 1,000 grams in a kilogram. And then we take the velocity, which was 30 meters per second, and we have to remember to square that here. So, 30 squared is actually 900. And then we multiply that by 0.15 and then by 1/2 or 0.5. And we come up with a kinetic energy of 67.5 joules. If you're interested in learning where the formula 1/2 mv squared comes from, this slide here shows just a sort of through an example how you can calculate and derive this result. I'm not going to go through it here because again, this is not super important for what we're going to do in this course, but it's a pretty straightforward derivation. Basically, I start with an example of pushing a chair for 3 meters using 100 newtons of force. So we know that work is force times distance. We can use Newton's second law and relate force to mass and acceleration. We also know some kinematics. The distance something moves that's accelerating is given by 1/2 at squared. So kind of putting all these three formulas together, substituting them into each other, we end up with that the work that we did here, the 300 joules of work, is equal to 1/2 mv squared, where m is the mass of the chair here and v is its speed. So this is one of several ways that we can derive the result. What we were talking about in the last few slides was technically called translational kinetic energy. That is kinetic energy of an object moving along a path. But something like this propeller here that's spinning, it's not moving anywhere, but obviously it's rotating. So the individual parts of the propeller are moving. And so this leads us to something called rotational kinetic energy. And again, I'm gonna skip over the derivation of how to derive the result. It's not that particularly interesting and it's kind of tedious. What we can do here is just show the results and compare it to our result from the last couple of slides. Remember that kinetic energy is 1/2 mv squared. So we've seen some of these substitutions before in this course. We take the m, mass, which remember is inertia, and we replace it with I, which is the rotational inertia of a rotating object. And furthermore, we replace velocity v with angular velocity omega. And that's really the simple way to think of this. Rotational kinetic energy, or K, it looks like K rot, right, for rotation, is equal to 1/2 I omega squared. So let's look at an example where we use both translational and rotational kinetic energy. Just think of this simple example of a bowling ball that's rolling down the lane. How much kinetic energy does a bowling ball have? Its mass is 6 kilograms and it rolls at 5 meters per second. So we have to recognize that this bowling ball is doing two things. It's moving from one point to another, so that's translational kinetic energy, which is 1/2 mv squared. But of course, the ball is also turning as it rotates, as it rolls. So that's rotational kinetic energy. And remember, that's equal to 1/2 I omega squared. So here's an equation to calculate the total amount of kinetic energy. Now, in order to continue our calculations here, we have to know what the rotational inertia of the bowling ball is, I. So this is, again, a case where we look it up in the table back in chapter 7 for the rotational inertia or moment of inertia of various shapes. And this is a solid sphere, right? A bowling ball is not a hollow shell, it's solid all the way through. So that has a value of rotational inertia equal to 2/5 mr squared. The other thing we can do here is omega. Remember, this is the rotational velocity of the bowling ball. Well, if we go back again to chapter 7, remember that omega is equal to the velocity of the outer surface of this ball divided by its radius. And the velocity of the outer surface is the same velocity as the ball has as it rolls, okay? Because that's how fast the outside of the ball is turning. That's the same as this speed v over here. So we can replace omega with v over r, and remember that's squared. So the nice thing here is a lot of this cancels. Notice we have an r squared here. Well, here's an r and it's squared here. So the r's completely cancel each other. Also, this 2 here cancels with this 2 up here. So we can cross those out. So we end up with k equals 1/2 mv squared plus 1/5 mv squared. And plugging in our numbers for the mass and the velocity that were given to us, we find out that the translational kinetic energy of the ball is 75 joules. And then this is the rotational kinetic energy of the ball. It's 30 joules. So the total energy of the ball is 105 joules. One of the points here is that a rolling object has more energy than a sliding object. And the reason for that is a rolling object has rotational kinetic energy. It has a different type of energy added to the total energy. Let's next change gears here and talk about a different type of energy called potential energy. So potential energy is an energy that's due to position, not due to its motion. So this is something completely different. So not only moving objects have energy, and remember, energy is the ability to do work, but any object that has height, in other words, it's lifted off the surface of a floor or a table or the ground or something like that, can also do work if it were to fall. So if we think of this situation here, we've got this rotating cylinder, and we've got a hanging mass here with a string that's wrapped around and around the cylinder. So and this mass is a height h above the ground. So this mass here, if we let it go, it's going to pull obviously on the string, and it's going to start to turn the cylinder, right? And as long as while this mass is falling, the cylinder is going to start turning and accelerating. So what's happening here is this hanging mass has the ability to do work, because think about what's happening here. This cylinder is given rotational kinetic energy. And remember, energy is the ability to do work. So energy here, if we think of it as force times distance, how much force can this hanging mass exert? Well, it exerts its weight, which is mg. So that's the force. And what is the distance over which this force can act? Well, it can fall a height h. So the energy in this object here is equal to mgh. Now the question is this energy mgh kinetic energy? Why or why not? Well, it's not kinetic energy, because before we let this thing go, there's no kinetic energy at all in the system. Nothing is moving. So this is a different type of energy. The energy of this hanging mass here is due not to its motion, but due to its position, due to the fact that it is off of the floor here by a height h. So this is what we call potential energy. Potential energy you can think of as stored energy that's due to position, not motion. And in particular, what we were talking about in the last example with the hanging mass, this is an example of gravitational potential energy. And so your textbook uses the letter U for potential energy. That's pretty standard in physics textbooks. And the little g under here is a subscript that reminds us this is gravitational potential energy. We're going to encounter other forms of potential energy later, in particular elastic potential energy. So U sub g is, we calculated on the other slide, is equal to mgh. So let's just do a quick example here. How much potential energy does a 1 kilogram block of metal have if it's lifted 2 meters above the floor? So U is just equal to mgh, which is 1 kilogram times 9.8 times 2. That's the height, 2 meters. And so this is just 1 times 9.8 times 2, which is 19.6. And the units here are also joules. All types of energy are going to be measured in joules. So another common type of potential energy is called elastic potential energy. The elastic potential energy is the energy that's stored in a stretched or compressed spring. So elastic potential energy in a spring equals its ability to do work. So the question is, how much work can a compressed spring do? Well, we know that work is force times distance. So the potential energy in a spring due to elastic potential energy is going to be equal how much force, times how much distance that spring can push with. The thing that makes this a little more difficult is that with a spring, remember the force is not constant. It varies. For the force varies according to Hooke's law. F is equal to kx. You remember this from a previous chapter. K is the spring constant, and x is the amount of distance the spring is compressed or stretched. So the more we compress the spring, the stronger the force gets. So this makes the calculation not quite so straightforward. So instead, what we can easily figure out is what is the average force of the spring as it's compressed in. So the average force, it turns out here, since this is a linear function with distance, the average force is equal to the initial force plus the final force divided by 2. It's just like averaging two numbers together. And since the initial force is 0 when it's out here, all we have to do is take the final force, which is kx, and divide it by 2. So all this comes to say that the average force of a spring is equal to 1/2 kx. So what we can do now is calculate the elastic potential energy in a spring. So U with a S, the S stands for spring, is equal to the average force times distance. All right, this is how much, this is the ability of the spring to do work. So the average force is 1/2 kx, and the distance is x. So when we multiply this together, we end up with 1/2 kx squared. So this is the formula we'll be using for the stored potential energy in a spring. And K is the spring constant, which we either have to figure out or it's given to us. And X is the distance of how much the spring is either compressed or stretched. One interesting application of elastic potential energy is a biomechanical example where we can talk about the elastic potential energy that's stored in tendons. So tendons connect muscles to bones, and they're like springs in that they're elastic. They can stretch and store elastic potential energy. So this stored energy is then used to help the animal walk or run faster using less energy. So the example here is showing a human foot. This is the calf muscle up here, and the calf muscle is attached to the heel bone by the Achilles tendon. And while we walk or run or jump, this Achilles tendon stretches a little bit, and like a spring or a stiff rubber band, it stores up some potential energy there that can then be released when we decide to push forward with our stride. Other animals have this, a much better advantage. For example, you can see in the ostrich, you can see the long tendons in its leg that give it a biomechanical advantage to be able to run faster and more efficiently than humans. And of course, the cheetah takes this to an extreme, right, with its ability to run greater than 70 miles per hour. There are several types of potential energy. In this course, we're only going to deal with gravitational potential energy and elastic potential energy. However, if you take Physics 102, you'll learn about electrical potential energy and magnetic potential energy, and also nuclear potential energy. There is also chemical potential energy, which is energy stored in molecular bonds. For example, in batteries, use electrochemical reactions to release energy, and also food. When we eat fuel or put gasoline in our car engine, that is an example of chemical energy. The next type of energy we're going to discuss is called thermal energy. So here's a quick activity you can do at home. Rub your hands together like is shown here. And what do you feel? And where does this energy come from? Well, you feel your hands getting warm, right? And as you probably guessed, this warmth or this heat that's produced comes from friction. Another example is if you take a book and slide it across a table, as shown here, it slows down and comes to a stop. Now, where did the book's kinetic energy go? Well, what happens here is friction, we know, slowed down the book and caused it to stop. It turns out that the kinetic energy of the book actually went to thermal energy or heat, kind of like the same thing with rubbing your hands together. So what is this new type of energy called thermal energy? It's the total amount of energy inside a substance due to the kinetic energy and potential energy of all the atoms wiggling or vibrating. All right, so thermal energy is a new type of energy for us. It's a little bit different because it's an internal energy. It's not something that has to do with where the object is or how fast the object is moving, like kinetic and potential energy. It's an energy that has to do with the internal state of the object. However, thermal energy, like all energy, is measured in joules. So I'm going to show you a couple of computer model simulations that will help clarify what thermal energy is and how it's produced by friction. One thing I'll mention before we look at the simulations is a model of a solid. We saw this earlier in the course when we talked about the elastic properties of materials. Remember, we talked about even something as hard as steel or diamond really is an elastic substance. And the reason for that is that the atoms of any solid, like for example, steel or diamond, are connected by bonds. And those bonds behave like tiny little stiff springs. And this means the atoms inside of a solid can actually move around and deform slightly. And so when these atoms vibrate back and forth, this is what we call thermal energy. So again, let's take a look at these videos. This is a computer program or model that simulates the motion of individual atoms inside of a solid. It's very convenient for getting a nice graphical picture of what thermal energy looks like. So in this canister here is a chunk or a crystal of argon. And argon is normally a gas at room temperature, but at very cold temperatures it freezes. And so this thing is set up right now to have a temperature of 1 Kelvin. Now that is only 1 degree above absolute zero. So this is about 450 degrees below 0 Fahrenheit. So at this temperature, argon is ice. It's a solid. And furthermore, all these little circles here represent individual atoms of argon that are held together by bonds. And you can see that, even at this cold temperature, they are slowly wiggling back and forth if you look real carefully. But basically at this temperature, there's very little, if almost no, thermal energy in this crystal. Now what we can do here is I can grab the heater down here and I can raise the temperature a little bit. So now you see the temperature went up to 10 kelvins. And so now, even though it's still a very cold chunk of argon ice, you can see that the individual atoms are wiggling and jiggling back and forth. This is thermal energy. So this piece of argon ice has more thermal energy than the other one did because of all this motion and jiggling of the atoms. And we can, keep adding more heat. We can go up to, this is 25 kelvins now, and you can see that they're really shaking around a lot. In fact, this is starting to become unstable, and if we keep adding more thermal energy, there will be enough thermal energy where the bonds actually start to break, and now you can see the atoms sort of slipping and sliding past each other. We're now into a liquid state. So we'll look at the phases of matter later in this course, but for now we just want to get a good picture of what thermal energy means. This is another computer simulation program that attempts to show how friction creates thermal energy. So the situation here is we've got two books down here, a chemistry book laying on top of a physics book. And in this picture up here, this is sort of a model of what the surfaces of these two books look like. So the chemistry book atoms are shown up here in blue, and the physics book atoms are down here in the green. So right now you can see that there's not a lot of thermal energy here. The individual atoms, you can see them wiggling back and forth a little bit, but basically there's not a lot of thermal energy. Now I can grab the chemistry book and I can bring it down in contact with the physics book and actually start rubbing it back and forth. And you can see as I do this, notice the thermometer, the temperature is going up, and we're creating thermal energy. So the motion of these of the atoms has increased due to the physical contact of them rubbing into each other, and that agitates the atoms and gets them moving faster. We're creating thermal energy, and what we would actually feel is that, when we rub these two surfaces together, just like when you rub your hands together, you would feel warmth, you would feel heat generated. So this is, again, what thermal energy is all about. So we saw in the computer simulation that friction produces thermal energy. So the work done by friction creates thermal energy. This new thermal energy adds to any existing thermal energy. Thus, what we're going to deal with is the change in thermal energy, and that's given by this equation here. So delta E thermal, all right, this is the change in thermal energy, is equal to the work done by friction. So in other words, if friction does 100 joules of work, then that creates 100 joules of thermal energy over here. Okay, so it's just sort of like counting money. All right, if we take $100 and put it in the bank, well, we increase our bank account by $100. So we'll talk about the money analogy more later. But to figure out how much work is done by friction, remember friction, we can show that as F sub k. This is kinetic friction, all right, because it's friction of motion. And we multiply that by distance, all right? Force times distance is work. So kinetic friction, remember, is calculated by mu sub k. That's the coefficient of kinetic, or it could be rolling friction as well. Just it's not static friction. And then N is the normal force, all right? So mu sub k times N is how we calculate friction. And then we have to multiply that force by the distance, delta x, the distance over which friction acts. So this here is how we can calculate the amount of thermal energy that was created whenever friction is at play. Let's go ahead and do an example that shows this, a relationship between friction and thermal energy. So here we've got in the picture, a man slides a 100 kilogram wood crate 5 meters across a wood floor. How much thermal energy is generated? All right, well, we know to figure this out, I can skip ahead here, the amount of thermal energy is equal to the force of friction times the distance. So we have to figure out the force of friction, all right? So remember, force of friction is mu sub k times the normal force times the distance. So we can figure out what mu sub k is. That's the coefficient of friction. We have to look in a table, and this goes back to, I think it was chapter 5, when we had the table of coefficients of friction. So for wood on wood, for kinetic friction, the coefficient is 0.2. The normal force of the crate, remember, this is a free body diagram of the situation here. While the weight is pulling down and the normal force is pushing up, these two forces in this problem are equal, right? Because this crate is not moving vertically, it's just sliding across the floor. So the normal force is equal to the weight of the crate, which is mg. So the mass of the crate is 100 times g is 9.8, gives us 980 newtons of normal force. So we can put that in here for n. Here's our 980. And then delta x is the distance involved, and that was given as 5 meters. So our answer is 0.2 times 980 times 5, which is 980 joules of thermal energy were created. And how would this manifest itself? Well, basically sliding this big heavy crate across the floor, the bottom of the crate is probably going to be warm after sliding across the floor. This is the same thing as rubbing your hands together to generate that thermal energy. Here's another example involving friction and thermal energy. Just one a little different because this one involves motion in the vertical direction. So a 100 kilogram fireman slides down a 5-meter pole at a constant speed of 2 meters per second. How much thermal energy is produced? So there's a couple different ways we can approach this problem. If you think about Newton's second law, net force equals ma. Well, we're told that he's sliding down at a constant speed. So our acceleration here is 0. So this right side of the equation is 0. Now the net force, let's look at a free body diagram of our fireman. There's his weight, all right, the force of gravity pointing down equal to mg. And the friction force, there's a kinetic friction force that is, slowing him down from just free falling, basically, right? So that is F sub k. So let's call this F sub k in a positive direction, minus his weight is equal to 0. So the friction force is equal to mg. We just solved this for F sub k. And mg is equal to 100 kilograms times g, 9.8. So the friction force here is 980 newtons. That's the same as his weight, by the way. These two forces are in equilibrium here, in balance. So the amount of thermal energy created is equal to the friction force times distance, right? This is the work that friction does here, force times distance. So we've got 980. newtons times 5 meters turns out to be 4,900 joules. So that's the amount of thermal energy produced as he slides once down this 5-meter pole. The last concept we're going to talk about in this part of the lecture is total mechanical energy. So let's imagine this scenario here. This is a ball up here. It could be like a baseball or something like that. And notice it's off the ground here and it's flying through the air, after it got hit with the bat or whatever. So the question is, what kind of energy does this ball have? Okay, well, let's not include thermal energy right now. Let's just talk about what's called mechanical energy. This ball has two types of energy. It has potential energy because it's off the ground, and it also has kinetic energy because it's moving. So added together, this gives us the total energy of this ball. So the definition here, total mechanical energy, is the sum of kinetic energy and potential energy. All right, and so what is mechanical energy? It's kinetic and potential energy, but not thermal energy. Okay, that's something different than mechanical energy. So total mechanical energy here is 1/2 mv squared, that's kinetic energy, plus mgh, that's the gravitational potential energy here. So in our last little example here, describe the total energy of a dropped ball. So here we see our ball falling from rest up there down to the bottom. So at the top, the ball only has potential energy, mgh, right? It doesn't have any kinetic energy until it starts to fall. When it's kind of down in the middle, right, in this position here, it has both kinetic energy, 1/2 mv squared, and it has potential energy, mg, and I said h over 2, because remember, this is the total height of the ball at the top. So in the middle, its height is half of h, so it's h over 2. And also its velocity here, I called it v sub mid, meaning that whatever the value of speed is right here, that would be the velocity we would plug in here. Now, when the ball gets to the bottom, it doesn't have any potential energy because it doesn't have any height. So all of its energy is now kinetic energy. So its total energy would be given by 1/2 m v final squared, where v final is the speed of the ball right as it hits the ground here. So that is our introduction to energy in this part of the lecture. In part 3, we'll look at the relationship between work and energy and how they can be used working together in the work energy theorems. I'll see you in part 3.